Okay, so random variables. A random variable just means that we've got a probability model and the outcomes are numbers. Okay, so that's kind of a small thing. We've been kind of thinking in terms of outcomes that could be numbers sometimes and other times not. But it turns out to be hugely helpful. Hugely helpful, for example, to think about if it's a coin flip, to have heads represented by a 1 and tails represented by a 0. And it's maybe a little bit of an exaggeration to say that the main reason for defining a random variable is so you can take its expected value. There are some other reasons as well, but that's a really big one. So one of the big things that we get when we represent our outcomes as numbers is we get the ability to compare them, to compare random variables to each other, and to compare a random variable to a certain situation. And expected value is what allows us to do that. We talked about expected values, and we also talked about expected values of a function in Math Camp in Unit 2. And if you don't feel like just completely all over this, I would go back and look at that Unit 2 video. There's a link on our webpage to it. I'm just going to sort of quickly hit the high points in this lesson here, relying on you to review the kind of more thorough treatment from Math Camp. Yeah. Okay. So just an example of using a random variable in a little political science model. I'm going to do the kind of what people sometimes call the playground bully model of responding to threats. It's sort of a workhouse model in the field of international relations. So what we're thinking about here is we've got country X here. And country X got attacked by its neighbor. Tanks rolled up to the border, shots are being fired. What's country X going to do? Is country X going to fight or not? Okay. In this very simple story, if country X doesn't fight, there's no uncertainty. What's going to happen is that country X is going to lose some territory. Okay, and so the payoff is going to be a negative t. That t is just going to represent the value of the territory that this belligerent neighbor is going to take if country X doesn't defend itself. Okay, so then the issue, the uncertainty comes in if country X does decide to fight in this story. Then the payoff is going to be a random variable. I think we'll call it x2. So the payoff is either going to be either the attacker is weak and country X doesn't lose anything. Okay, 0 is a high payoff in this little story here. You know, it's this violence in international relations is a nasty business. The best you can do is break even here. So if I'm country X and I decide to fight and the country that attacked me is weak, I get a payoff of 0, and let's have the probability of that, just represent that with the letter P. Okay, so I'm making a little table here of the values that random variable X can take with the corresponding probabilities. And so the other possibility, if the attacker isn't weak, they are strong. And if country X fights and the attacker is strong, that's bad news for country X. They lose their territory, negative t, and they lose some additional costs of fighting. Okay, so C represents whatever else happens. Their military gets destroyed, their capital gets burned, who knows what happens. So that's the other part of the situation. And that happens with probability 1 minus p. Okay, so just kind of belaboring the issue here, this is an example of a random variable, okay? And it's a random variable because we are representing the, actually that's not quite, drew my red circle to include something that's not part of the random variable. What I've got in red here, should be red, this is the definition of a random variable. It's an uncertain situation. We're representing the outcomes with numbers. That's really the important thing. And the probabilities that are associated with those numbers follow the Kolmogorov axioms, and we can do all the things that we've learned how to do so far with those probabilities. Okay, so we want to know what should country X do, and the way we would conventionally understand that situation is we would calculate the expected value of this random variable and compare it to the certain payoff here of not fighting. Okay, so let's just kind of go through that exercise. So we should fight if the expected value of X is greater than negative T. And let's sort of remind ourselves what the expected value is. We take each possible outcome, we multiply it by the associated probability, and we add them up. Okay, so the expected value of X is, I get 0 with probability P, so I'm multiplying that, or I get this negative T minus C with probability 1 minus P. Okay, so this part is expected value of X there. And the question rule here is, the question that we're interested in is whether this is greater than negative T or not. So just to tie up this example, I've got a 0 in this first term, distributing the 1 minus P over those two terms. Actually, I think I'm going to factor out a negative 1 at the same time because too many negatives floating around. So when I factor out the negative 1, I'm going to switch the direction of my inequality. I'm going to get 1 minus P times T plus 1 minus P times C. And I factored out the negative 1, so that should be greater than T. Okay. Taking the T terms over to the other side, 1 minus P times C is less than T minus T plus P times T. That looks like PT. So we should fight if this is true. If C is less than the ratio of PT over 1 minus P. Okay, so fine. That's, if we were really interested in the situation, we could think about what it would mean for C to be a big or a small number here. If the costs of fighting, the additional costs of fighting are relatively low, that would work in favor of the inequality going the direction it's supposed to. If the value of the territory is high, similarly, that should make us, push us toward fighting. Also, if P is large relative to 1 minus P, that means the country is relatively more likely to be weak than strong. Those are all reasons to fight that are picked up in this little equation here. The point I'm just making here is, the reason why I'm doing this example is we took a situation where there was uncertainty. Because we represented the outcomes as numbers, we could calculate the expected value of that situation and compare it to another situation whose outcome we're also representing as a number. Okay. End of example. Let's just remind ourselves for a given random variable X, that I'm gonna make that same little table here. X takes values X1, X2. How many values does it take? Oh, n of them, with probabilities P1, P2, Pn. So just kind of a general random variable. Here we calculate the expected value of X. P1 X1 plus P2 X2 plus dot dot dot. P1, Pn times Xn. And if we want to write that in a kind of a more compact form, we would just say that that is the sum as I goes from 1 to n of Pi Xi. If you don't like the summation, you can always just write it out like that. And if you feel like one of these summation signs is staring you down in a way that you don't like, you can just slay that dragon by writing out the terms. All right. Comments on expected value. Again, stuff I think I talked about in a little more detail in the math camp lessons here. But the kind of amazing thing about expected value is see how all of the information here that's in the definition of the random variable here, all the probabilities and all the outcomes all get combined in the expected value. Okay, so that's one cool thing. Another thing that sort of helps people wrap their brain around expected value is it is the idea of a weighted average here. We're taking an average of all the possible outcomes that can happen, but instead of taking just a kind of a simple average where we add up the outcomes and divide by how many there are, that would be giving them equal weight. Here, we're letting the weights be the probabilities. Okay, so if the outcome's more likely to happen, it's getting multiplied by a bigger number. If it's less likely to happen, it's getting multiplied by a smaller number. And final thing I want to point out about just about expected value. Maybe a few final things. Okay, one of the final things is this E. It's an operator. Okay, it's telling us to do something the way an integral sign is telling us to take an integral. It's an operator that operates on a random variable. Okay, so if you want to take the expected value, you need a set of outcomes and a set of probabilities. You're going to see that we will sometimes be taking the expected value of something that's a number, and the way we think of that is like that's a random variable that takes the value of the number with probability 1. Okay, but it's an operator in general that operates on random variables. Operates on and yields a number. Okay, so X here, that's a random variable, that's a complicated thing. We have to sometimes be careful with it in ways that I'm going to talk about in a minute. But once I take its expectation, then it's just a number. It's a number that I can compare to other numbers. I can do sort of normal algebra on it. Once we've taken the expectation and we have a number, things get simpler. Okay. Final sort of observation on random variables, just some notation that you'll see really. Okay, so one way to write the expectation of X is what I've been doing, this expectation operator with a random variable after it. Other kinds of notation that you might see, sometimes you'll see this, like X bar, okay? And just like with the different notations for derivatives, the different notations kind of emphasize different aspects of the thing. The E notation emphasizes that this is like something we're doing to a random variable and transforming it into a number. The X bar notation kind of draws our attention to the idea that it is a number. Okay. Another symbol that's commonly used is this. That's the Greek letter mu for mean, because mean is basically a synonym for expected value. Tends to be used sometimes in slightly different contexts, but there is nothing that's true about an expected value that wouldn't be true about a mean. So these are all just different ways of writing the same thing. Expected value. Also, sometimes just say the expectation of, or the mean of X. Okay. See you in the next lesson.